Hello, everybody. So now what I'm going to do is I'm just going to go through the Mobius assignment and hopefully just explain how to do each question and logically why it is that way. Hopefully this is legal. I'll ask Mr. Spetskalis or Sean on Monday if this is legal and I can do this for future assignments. Hopefully it is legal, but we'll see. If not, I'll just ask like it's happening for the third assignment. Yeah. Anyway, let's start. So which of the given sequences are monotonic for all n greater or equal to 1? And let me just make sure that I can annotate. There you go. I should be able to write on here now. Perfect. So monotonic. So monotonic means that it is always increasing or always decreasing. So let's start with here. So over here, we can see or check that this is not monotonic because it's the first term, for instance, is going to be root of 1/2. And this is monotonic is what I'm about to say. And so that's going to be the first term, which is going to equal to 1/4. And the second term is going to equal to root of 1/4, which is 1/8. And so on and so forth. And we're going to see that this is going to be decreasing. So then clearly, this would be the correct answer. Then if we continue, we're going to reach our next one. So an is equal to 3 plus 8/7n. And again, we're just going to check whether this is true or not. So for the first term, if is equal to 1, we're going to get 3 plus 8/7, which is going to be equal to, 4 and 1/7. 4 and 1/7. The second term is going to be 3 plus 8/14, which is going to equal to 3 and 8/14, which is smaller than our second term. Our third term is going to equal to 3 plus 8/21. And again, that's going to be smaller than our second. So we can clearly see that this is also monotonic because it's always decreasing. Then what we're going to do is sine 1/n. And we know that this is not monotonic because the sine wave always goes up and down. So clearly it's going to have some highs and lows. It isn't monotonic. And finally, we have 1 plus -2 to the power of n/n. And we know this one's not monotonic because -2 is going to keep on changing. It's either going to be negative or positive. Negative and positive. And because it's going to have negative and positive, we know that this is also not monotonic. And so that's how we would figure it out here. Next. So now I will clear the board, clear all drawings, and let's start again. So here, which of the following sequences an converges to 0? So basically what we're thinking about is whether the limit of the sequence when n is approaching infinity is 0 or not. And let's go through each one. So over here, this sequence would approach 0. And there's two ways of knowing this. The first way, and the way I kind of do it, is I see, well, look over here. We have n squared. So the exponent on the bottom is 2. And the exponent on top is 1. Therefore, the n on the bottom is going to reach infinity faster than the top. And that's why if you have infinity over something, or something over infinity to be more exact, it's going to be 0. But a more formal way of doing this and proving this is what we did in class. We're going to take n squared out of the brackets from each. So we're going to get, if we do it formally, a limit at n approaches infinity. On the top, we're going to get 5/n times n squared over, actually, that's not what I want to do, sorry. We're just going to get, on the top, we're going to get 5n, and on the bottom, we're going to get n squared, 1/n squared plus 5. Over here, we're going to get n's are going to cancel out. And so at infinity, these are not going to really matter. This is going to be 0. So at infinity, this is going to equal to 0. And just so we're going to get infinity here. So we see that this is going to 0. Hopefully that made sense. Over here, we are going to get that this is not going to go to 0. And that's because the exponent on top is bigger than the exponent on the bottom. On top, it's 2. While on the bottom, it's 1.5. 0.5. And again, we could prove it the same way we did on top by factoring out the largest exponent and seeing that they cancel out. Okay, now we can go on to this case. So over here, again, the exponent on the bottom is bigger than the one on top. So this is going to go to 0. And again, we could prove that by factoring out the largest exponent, but it's already factored. So here, this would go to 0 to infinity. This would go to 0. This would become infinity. 1 over infinity is 0. Over here, it's not going to go to 0. This is going to go to infinity. And the way we can do this is, again, just by factoring out. So what we're going to do is we're going to factor out 6 over n on this side. So this is going to equal to 12, or let's go like this. So it's going to be 6 to the power of n times 2 to the power of n. And the way I got that is 12 is equal to 6 times 2. And then 6 times 2 to the power of n, we could just get n's on both of them, is going to equal to 6 to the power of n, 1 plus 5 over 6 to the power of n. 6 to the power of n and 6 to the power of n are going to cancel out. This term over here is going to become 0 at limit n equals infinity. So we're going to get 2 to the power of n over 1. And 2 to the power of n goes to infinity. Now be careful, and I just want to quickly mention this. If this term over here, if it wasn't 2, but it was, for instance, 1/2 to the power of n, then this would be a limit of 0. So just a good way to remember, and you can imagine the exponential function if you want and check in Desmos. So a to the power of n goes to infinity if a is greater than 1. And then if a is smaller than 1, so if a to the power of n where a is bigger than 0 but smaller than 1, then the limit is going to be 0. And again, you can check me on this if you want. Just open up Desmos and type in your exponential function. And if you have like a is equal to 1/2, you'll see that the function is something like this. And if a is bigger than 1, it's going to be something like this. General trends. Yep, so that's it for this page. So let's click next. Perfect. So now we reach this one. So over here, what is it asking? It's asking us find a1 term, so find the first term, so a1 equals to something, such that this sequence over here is decreasing. So as an example, if a1 is equal to 0, then a2 is going to equal to 0 plus 4 divided by 2 is equal to 2. A3 is going to equal to 2 plus 4 over 2, which is equal to 3. A4 is going to equal to 7 over 2, again 3 plus 4 divided by 2, so 3.5, and we see that it's increasing. Now there's two ways of doing this. The first way is to just plug in each value and see if it's increasing or not. A more efficient way that we found is that you can find the limit of an plus 4 over 2. And the way you find the limit, if you remember in class what we said, is the way to find limits for this is like this. So we know that an at infinity will have some limit, and this limit is L, right? Now an plus 1 is going to have that same big limit. And why is that? Well, an plus 1 is just the continuation of our an. And so they're both going to be going towards the same thing, and that's why they're going to have the same limit. So now an at its limit will be L, so L plus 4 over 2, and an plus 1 at its limit is also going to be L, and that's why this is equal to L. And now if we calculate the limit, what is L going to equal to? We're going to get L plus 4 is equal to 2L. 4 is equal to L. So the limit here is 4. Okay, great. So the limit is 4. So now what we can kind of do is we can plug in into each section, or for each a1 term, we're just going to plug it in and see if it's smaller than 4 or bigger than 4. If it's smaller than 4, then it has to increase to reach that limit of 4. If it's bigger than 4, then it has to decrease to reach that limit of 4. So let's take a look. So if 5 is our limit, so if if a1 is 5, then we're going to get 5 plus 4 over 2 is equal to 4.5. Now 4.5 is bigger than 4. So as the sequence continues, the limit is 4, so it's going to have to go down. So this, if a1 is 5, it is going to decrease. Now, what if it's negative 4? Well, if it's negative 4, then we're going to get negative 4 plus 4 over 2 is equal to 0. So if the first term is 0, it needs to increase to get to 4. So therefore, this sequence, if a1 is equal to negative 4, will not be decreasing. It will be increasing. Same thing with 2. So if we get 2 plus 4 over 2, it's going to be 3. 3 needs to increase to reach to 4, so therefore it's going to be increasing. And if it's 7, we're going to get 7 plus 4 over 2 is equal to 5.5. And 5.5 needs to decrease to reach 4. So therefore it's going to be a decreasing function. Check. And that's how this page works, or this question works. Okay, now we reached our next. Clear all drawing. So consider the sequence an is equal to 6 minus 3n over n. For which inequalities will the terms of an be within epsilon equals 0.01 of its limit? So basically we're asking for which terms of n, so when n, let me just start drawing again, when n is greater than what term will the epsilon, or the distance from its limit, be smaller or equal to 0.01. So again, if we remember our image, the way we can visualize this is, I'm just going to draw it over here. So if here we have our x and y, so x, y, and over here we have our limit. So this is our limit, and then our sequence goes something like this, right? So then if we put an n somewhere here, then this will be its epsilon. Epsilon is equal to 0.01. So we need to find for this sequence, past which n we need to pass so that the epsilon will be within or smaller or equal to 0.01. So the way we can figure that out is two things. So first we need to figure out the limit to see where it's going. And then we need to calculate what the n must be. And you can kind of think of that as, we can go through that whole sequence. So if we want to be very formal about it, we would say first we need to prove this for let epsilon be greater than 0 and be arbitrary, then we must be able to find k such that an minus l is smaller than epsilon when n is greater than k. But here, because we're just working to solve this, we don't need to be that formal, but if you want to, it's good to be that formal. So then what's our limit? Our limit is just going to be negative 3 over 1. That's what we're going to reach. So then it's going to be negative 3. Our L is equal to negative 3. Then we're going to take absolute value of 6n minus 3n over n minus 3. Absolute value is smaller than epsilon, or in our case, it's going to be 0.01. And where did I get this from? Well, that comes from our general expression that we would need to use, which is going to be our sequence. So our an, so the distance between our an and our limit should be smaller than our epsilon. And that's what I did here. So this is our sequence, this is our limit, and this is our epsilon. Now what we just need to do is we need to isolate for n. So we're going to get absolute value of 6 minus 3n over n plus 3n over n, and the plus here is because it's negative, is smaller than 0.01. So negative 3n and plus 3n, they cancel out, so we get 6 over n. Absolute value of that is smaller than 0.01. We know this is always going to be positive because n is always going to be positive, so it's 6 over n is smaller than 0.01. Then we just isolate for n. So n is going to be greater than 6 over 0.01. And then what do we get? We get, I'm going to be lazy, I'm just going to use a calculator. I know we could do this in our head, 0.01. It's going to be 600. So n must be greater than 600. There you go. So now we just see which of these are greater than 600, because again, if this was 600, then anything past it will also be within that epsilon of 0.01, right? The distance is either going to be smaller or equal to it, right? Because if we put here, if this is, for instance, we have 660, then the epsilon is smaller, but it's still within that range of 0.01. And in our case, it's just going to be all of them. I hope this makes sense. So let's go next. Okay, so let's clear all drawings. Okay, so now we have this example. So which of the following are upper bounds for the sequence an? And here we have, this is I forgot what the sequence is called, but we have a sine function and the upper bound. So what we're going to do here is we are going to use the squeeze theorem. So we're going to say that sine n is smaller than 1, smaller or equal to 1, or bigger or equal to -1. Now we want to kind of strive to reach this over here. So we're going to multiply both sides by 6n. So 6n is smaller or equal to sine n times 6n, negative 6n is over here, and bigger or smaller than equal to 6n. Then we're just going to divide both sides by 7n plus 5. So negative 6n over 7n plus 5 is smaller or equal to 6n sine n over 7n plus 5, which is smaller or equal to 6n over 7n plus 5. And there you go. So now we know that 6n times sine n over 7n plus 5 has to be smaller or equal to 6n over 7n plus 5. And this is basically our bounds, right? So these are our bounds for our sequence. And now what we can do is we can calculate the limit of this sequence over here. And the limit would be just 6 over 7. This would be its limit. And then what we can do, if we want to be very thorough, we can check whether it is an increasing function, an increasing sequence or a decreasing sequence, and then know if this is its upper bound or its lower bound. So let's check that quickly. So if n is equal to 1, then this is going to be equal to 6 over 12, which is 1/2. If n is equal to 2, then it's going to be 12 over 19. And then if it is n is equal to 3, then it's going to be 18 over 26. And we can clearly see that this is increasing because here it is 1/2. Then it is 12 over 19. Well, that's bigger than 1/2. And then 18 over 26, I presume, is bigger than 12 over 19. So that means our sequence goes something like this, and its limit is 6 over 7. So that means that it is an increasing, and this is the upper bound of this over here, which means that this is the upper bound of here. Now, what we're looking for is which of the following are upper bounds. So 6 over 7 is the least upper bound. And if you remember what that means, it just means that there are multiple upper bounds. Sorry for my bad handwriting. So there are multiple upper bounds if we just take a function or a sequence over here. Its biggest upper bound is over here. This is where it starts. But this is also upper bound because it's always going to be smaller or equal to this, like over here. So if we take a line, this is its upper bound, and this is its upper bound. But this point over here where it started is just its least upper bound. So now what we're looking for is just things that are bigger or equal to 6 over 7. So 2 over 7 is smaller than 6 over 7. 3 over 35 is smaller than 6 over 7. 3 over 7 is smaller than 6 over 7. But 13 over 7 is bigger than 6 over 7. That means that it's also going to be its upper bound. Cool. that's how this page works. And hopefully I explained it well. If not, again, you can just leave comments on my video, and hopefully I won't be too lazy to check. So better just to DM me. But on the other hand, if everybody DMs me the same question, that's going to be kind of not fun for me. Okay. So leave a comment, I guess, or just ping everybody, and then I will do that. But yeah, let's continue. So now, for which of the following sequence can the monotonic sequence theorem be used to prove convergence? So if we remember, the monotonic sequence theorem states two things. It states that if a sequence is both monotonic and it is bounded, then we can use the monotonic sequence theorem to prove that it is converging, or aka it has a limit. So we need to prove that, we need to see that it's both monotonic and that it's bounded. Okay, so let's check the first one. So the first one, it is monotonic, I believe. It has a limit of 1, and I think it's always going to be smaller, but we can check. So let's see. So it goes, if n is equal to 1, then this function is going to be 6 over 7. If it is 2, it's going to be 11 over 12. So it's always increasing. And so its bounds are going to be 6 over 7 and 1, because that's its limit. And so it is both monotonic and bounded. So then we can use the monotonic sequence theorem. Check. Then we can check root of an. So it does have a limit, which means it is going to be bounded, and its limit is going to be, I believe, 1. So it's going to be root of 4, then it's going to be root of 2, then it's going to be root of 2. And I believe that that does just limit to 1, but this also shows that it is monotonic, decreasing, and it is bounded. So then, therefore, we can use the monotonic sequence theorem. Check. Then we have over here 1 over 4n squared plus 5. So this has a limit of 0, because n squared will reach infinity, and 1 over infinity is 0. And then that means which means that it's bounded, because it's the first term will be its highest limit, 0 will be its lowest limit. Limit, I use limit interchangeably here. Remember that its highest bound is going to be the first term, and its lowest bound is going to be the 0. Finally, I think it is monotonic. It's always going to be decreasing, and we can check that. So if n is equal to 1, it's going to be 1 over 9. If n is equal to 2, it's going to be 1 over 21, which is decreasing. So we should be able to use the monotonic sequence here as well. And this one, this can't be it, because it doesn't have a limit. It's always going to be increasing, but that means it doesn't have an upper bound. And how would I know that it doesn't have a limit? Because on top, n squared is going to go to infinity. Therefore, we can't use the monotonic sequence theorem here, and that's why we don't check it. Next. Okay. And this is the hardest one, in my opinion, just because it's very conceptually hard to understand. So first, before I dive into anything, let's just read it and understand what it's asking. So given the sequence an is equal to 2n minus 6 is over 3n plus 4, which converges to L, which tolerances, epsilons, will be satisfied in the statement an minus L is smaller than epsilon if we assume that n is greater than 20. So before we start this, let's visualize what this is asking. So what it is asking, so again, I'm just going to draw my graph. And you know what? I will make the lines straight for sure now. So here we have 1 line, 2 line. So that's our graph. We're going to get x, this is going to be y. And now what is happening here? So let's draw some sequence. There is our sequence, and it is going to have a limit. Let's make that limit red, and also a straight line. So now what we're going to do is we're going to go here again. Let's make it black again. So over here, we are going to have some n, right? And for this n again, we are going to have some epsilon, which is the distance between the limit and n. So which tolerances will be satisfied in the statement if we assume that n is greater than 20? So what we kind of want is, if our tolerance is something, if the tolerance is going to be smaller than it is, then for n greater than it, it won't satisfy. That's not a good explanation. I'm sorry. Okay, so keep this in mind while we're working, and then I'll explain after we solve it. But in essence, what we're looking for is if n is greater than 20, then some epsilon is the epsilon, or the distance between n and its limit, is going to become smaller and smaller. So it's going to become smaller, and then even smaller, and then even smaller. And so those epsilons will become smaller, won't be satisfied. On the other hand, if we have something that is smaller than here, then n, the sequence, will still be with, and will still have that distance. It will still be kind of within that distance. It will still satisfy, because if it's any smaller than it, then then it's already not within that distance. But if it's bigger, even though it's bigger than that epsilon, it still satisfies this epsilon, because when you think about it, what the epsilon is saying is that it's within that distance or bigger than it. So that's why we're basically looking for n's bigger than it. And we'll see what I mean by this when we get there. So first, we got to find, so this is going to be very similar to a previous one we did, where we just needed to find the n's for a specific epsilon. In this case, we're basically finding some epsilons for these specific n's. And again, we're just going to be using the an, which is our sequence, minus l, which is our limit, is smaller than our epsilon. So in this case, we need to find our limit. Our limit is just going to be 2/3, because over here, hopefully that's good. If we need further explanation, just DM me. So let's put it in. So then we're going to get 2n minus 6 over 3n plus 4. That's not a good 4. Plus 4 minus 2/3, which is our limit, should be smaller than some epsilon. So then 2n minus, so let's simplify this. So we're going to get absolute value of 2n minus 6 over 3n plus 4 minus 2/6. So basically first 2/3, that's a 3. What we need to do is we need to find a common denominator to be able to subtract these. So we just need to cross multiply here in essence. So we can get 6n minus 18 minus, and then 2 times 3n plus 4. So it's going to be minus 6n minus 8 over a common denominator of 9n plus 4. And we take the absolute value of this is smaller than epsilon. So these 6n's are going to cancel out. And this is going to be plus 8 over here. I made a mistake because 2 times 4 is 8. But when we open up the bracket, it's going to be negative 8. So negative 18 minus 8 is negative 26. So we're going to get negative 26 over 9n plus 4. The absolute value of that is going to be smaller than epsilon. Now we know that 9n plus 4 is always positive because n is always greater than 1. So if we want to remove the absolute value signs, the 26 is just going to become positive. So we're going to get 26 over 9n plus 4 is smaller than epsilon. Then we need to isolate for n to figure it out to kind of meet this condition. So we're going to get 26 over epsilon is smaller than 9n plus 4. And now 26 over epsilon minus 4 is smaller than 9n. Finally, 26 over 9 epsilon minus 4 over 9 is smaller than n. And now what we kind of do is this is the epsilon. So for whatever n we get, we want to find our epsilon, or the distance that it is from it. This is it. Now we need to assume that n is greater than 20. So what we're looking for is an epsilon, in essence, which is greater or equal to when n is 21. And the reason it's 21 is because n always has to be a whole number. That's why n is going to become 21. So then what we're going to do is we're just going to plug it in here, and the epsilon just has to be great, because it would, if n is greater than 21, it would satisfy all of them. I'm not explaining this well, but let me finish it, and then hopefully I can explain it a lot better again. So then what we're going to do is we're going to say that 26 over 9 epsilon minus 4/9 should be greater or equal to 21. Greater or equal to 21. And 21 again, because n always needs to be a whole number, so 20.3 would not work. And so then we're just basically isolating for epsilon. So we're going to get 26 over epsilon minus 4 is greater or equal to 21 times 9. And 21 times 9 is 189. Is 189. 189. Then we're going to add 4, so 26 over epsilon is greater or equal to 193. And then epsilon is smaller, equal to, should be greater or equal to, 1 sec, we'll figure this out. Oh, because it should be smaller or equal, 1 sec. We'll figure this out in a sec, and I'll explain it a bit very well. But 26 over 193. So now what does this mean? That our epsilon should be, I messed up the sign here somewhere, but in essence, the way you should think about this is, again, so let's say that this is 20. We get some epsilon for it, which has this range. And what we want is which tolerances will be satisfied in the statement. So if the difference between these two, for instance, is 4, then tolerance of 3 would not be satisfied if n was, for instance, 23, right? Because it's smaller, so it doesn't satisfy this tolerance of 4. But if n, for instance, was 10, then that tolerance of 4 would still be satisfied, because the distance would still be greater than 4. And so that's why it would be satisfied. If you don't get it, text somebody at the chat, and maybe somebody can explain it better than me, because here I am clearly struggling to explain this, and I'm sorry, but hopefully you kind of understand. So now in essence, we're just looking for an epsilon, which is going to be greater than 26 over 193. And so 26 over 193, 26 divided by 193 is going to be about 0.13. So this is 0.13. And so what is smaller than that? So what we're going to get is we're going to get what is smaller than 0.13. Yeah. Okay, for this question, I'll probably make, but that's kind of the point. And then you would see which is smaller. I clearly messed something up here, but that's kind of the way you need to think about it. And again, other people will just point out in chat and tell me how I'm wrong, and that's totally fine, because here I really did a poor job of explaining. But hopefully that clears up most of the confusion in the assignments and for questions. And yeah, that's it. Thank you for listening, and hopefully it was helpful.